Well, hello everyone. It's Friday, April 17th, I guess, and it's a nice snowy day here in Northwest Ohio. Been snowing since late last night. Got a few inches on the ground so far, so gotta love the snow, I guess. Today we'll start Chapter 7, where we'll look at oxygen transport, both diffusion and consumption by the cells found in tissue, and we'll apply this to things like bioartificial organs and applications in tissue engineering. So lots of good usages for the material in Chapter 7. And Chapter 7 just builds on what we've already talked about in Chapter 5 and 6. So not a lot of new material. The only new thing would be the role of hemoglobin and how we count for oxygen consumption by the cells. Also, before we start the lecture on Chapter 7, I'll go through the solutions for Chapter 14. Or not Chapter 14, for Homework 14. Sorry about that. Homework 14. So let's get started. Okay, let's take a look at the solutions to Homework 514. And the first problem was problem 520. And basically, it's one of these hollow fiber type systems. We've got fluid flowing through a small tube, and in this case we've got an enzyme, which I denote by E, that coats the surface of the enzyme, or coats the surface of the tube, and the fluid coming in has a solute that reacts via the enzyme and gets converted into something else. And we're also told that the reaction rate is instantaneous, so this is a very fast reaction occurring at the surface relative to the mass transfer rate. So the whole process is mass transfer controlled, and we're also asked to find the fraction of the incoming solute that's removed, which I call little f, and the way you get that, the fraction removed, would be how much is coming in, which would be QCA in minus QCA out. So this is the actual amount of that solute that's been converted, and if you divide that by the amount coming in, then that would be the fraction of that solute that's been effectively removed by this process occurring on the surface of the tube. So that means then that the surface concentration of the solute CS is equal to 0. And from the molecular weight, we calculate the diffusivity from equation 535, so we get that number there, 7.35 times 10 to the minus 6 square centimeters per second. And then for the given flow conditions, you can show that the Reynolds number is just about 29, which tells you have laminar flow within the tube, and the Schmidt number comes out to be 940. And then using equation 5169, that's our go-to equation for mass transfer coefficients and laminar flow in a cylindrical tube. You can show that the mass transfer coefficient is 3.82 times 10 to the minus 4th centimeters per second. And then the following equation can then be written, which expresses the fact that the overall solute material balance from the entrance to the exit of the tube must equal the amount of solute reacted at the surface of the tube. So here's just the relationship of the actual mass transfer rate that happens, and we kind of went over this equation back in Chapter 5. And if you just rearrange this equation, you can get equation 5160, which is really the final equation that you would use in this problem. You could skip all of this up here because we've already done all of that, and we obtain equation 560, which with CS equal to 0 looks like this. And then you pop in the numbers, and this then tells you what the concentration of the solute is in the fluid flowing out of the tube. And then from our definition of the fractional removal, you would write that like this, and you get the number 0.32, which is the correct answer. Now the next problem is problem 532, kind of similar to what we just worked, but in this case we're told that we have a hollow fiber module with activated carbon particles in the shell space. and a toxic material coming in with the fluid into each of the hollow fibers. And what's going to happen is that at the beginning of this operation here, the activated carbon has really high capacity for that solute. So if the solute can make it to the wall of the hollow fiber, it's effectively just removed instantaneously, which means then that the concentration of the solute is 0 at the wall, as I state right here. And then the percent removal of each hollow fiber will be the same, since the plasma flow rate and the enzyme loading for each hollow fiber is assumed to be the same. And we only need to focus then on what happens in one hollow fiber. And then the flow rate of the plasma in a given hollow fiber is given by this equation. So we have to take the given volumetric flow rate to the hollow fiber module and divide that by the number of hollow fibers, which gives this volumetric flow rate for each of the fibers. And then we're going to need the average velocity of the plasma in the fiber in order to calculate things like the Reynolds number. So we can do that by this definition shown here. Plug in the numbers, that comes out to be about a half a centimeter per second for the average velocity of the fluid. Next we can calculate, as shown at the top of the next page, we calculate the Schmidt number rather, shown right here. We get a Schmidt number of 2,604. We calculate the Reynolds number, about 1.74, so we know we have laminar flow. And then we go to our go-to equation, which is equation 5169, to calculate the mass transfer coefficient, which is shown in the next series of calculations here. Plug in all the numbers, you get a Sherwood number of 4.107. Calculate the mass transfer coefficient. Comes out to be 0.000462 centimeters per second. And then we go to equation 5160, and with the surface concentration being equal to 0, that equation looks like this right here. Pop in the numbers, and then the percent removal, as I mentioned in the previous problem, would be 1 minus Ca out over Ca in, and if you want the percent, you would multiply that by 100, so we get 97.33%. And the next problem shown here is problem 534. Once again, we have a hollow fiber system. We have endothelial cells that are immobilized, forming a confluent monolayer on the inside surface of the fibers, and on the surface of those those cells express an enzyme which instantaneously removes a particular toxic material in the feed stream. So that makes, once again, our concentration at the surface equal to 0. We find the diffusivity in the toxin in water at 37 degrees C from equation 535, so you should get that number that I have shown here. The viscosity of water at 37 C is 0.691 centipoise, and the plasma has this viscosity. And then using equation 542, we can find the diffusivity for the toxin in the plasma, so we have to adjust for the higher viscosity of the plasma relative to water, and we get this particular value here for the diffusivity. And then the flow rate of the plasma in each of the fibers is given by this equation, so we get 0.0125 cubic centimeters per second. And the average plasma velocity in a hollow fiber can then be calculated, as shown at the top of the next page. So we go to that calculation. There's our average velocity within a particular fiber. Then we calculate the Schmidt number. We get 4,311. Calculate the Reynolds number, about 68. So we have laminar flow again. We use equation 5169 to calculate our mass transfer coefficient, which is shown down here. So here we calculate the mass transfer coefficient, comes out to be 0.0024 centimeters per second. And then we can calculate the exiting level of the toxic substance using equation 5160 with a surface concentration equal to 0. Okay, and then from equation 5169 we can calculate the ratio of the concentration of the toxic material out relative to the concentration in, and that becomes 0.834, and we get the exiting toxin concentration is 0.834 times the entering concentration, and we get this particular concentration here, 0.00834 moles per liter is our final answer. And then the last problem in this homework set is equation 538, which is another spill type problem. So what we have here is chloropicrin, which also in the military literature is given the symbol PS. So the PS mass transfer is happening from the spill. We're told the spill is 0.8 feet by 2.5 feet, and we have wind at 10 miles per hour flowing over the surface in the direction of the length of the spill, and we want to calculate the mass transfer rate of the chloropicrin. And we're given a lot of English units in this problem, so one of the things you'll want to do is convert these into metric units, and we'll estimate the value of Km from equation 5135, assuming that we have laminar boundary layer flow over that flat surface. So the first thing to do is to calculate the Reynolds number, which is shown up here at the top of the next page, and we calculate then a laminar Reynolds number for flow over a flat plate of 217,000, which is less than the value for which you transition to turbulent flow, which is around 300,000. Calculate the Schmidt number, which comes out to be 1.784, which makes sense since we're talking about gas mass transfer of the chloropicrin. And then the mass transfer coefficient for laminar boundary layer flow over a flat plate is given by this expression right here. Pop in all the numbers. We get a Km of 0.421 centimeters per second. The mass transfer rate would be the surface concentration times the surface area of the spill times that mass transfer coefficient, assuming that outside the mass transfer boundary layer the concentration of the chloropicrin and the air flowing by is essentially zero, or much smaller than the saturation value. So when you plug in all the numbers, you calculate an evaporation rate of about 595 grams per hour. Okay, in today's lecture we're going to start chapter 7, which is called Oxygen Transport in Biological Systems, and another distinction that we'll want to bring to bear in this discussion of oxygen transport is we'll also have to consider the oxygen consumption of the cells along with the oxygen diffusion through the tissue. And before we can do that, we need to figure out how we talk about the amount of oxygen in tissue and in fluids such as blood. And to do that, we have to go back to thermodynamics and review a little bit about gas-liquid equilibrium. So what I have down here is I just show a closed vessel, say with blood in it. The round circles just represent the red blood cells. Here's the interface between the blood and a gas up here. And in that gas we have a partial pressure of oxygen. And remember, from thermodynamics, the partial pressure of oxygen, or a partial pressure of a solute in a gas, would equal the total pressure times the mole fraction of that solute, or in this case oxygen. So that's how we define the partial pressure. And if we let this system come to equilibrium, then for a given partial pressure of oxygen up here in the gas, we can talk about how much oxygen is actually dissolved in the fluid portion of the blood, which would be the plasma. Now, I'm just going to point out a distinction here. The red blood cells contain hemoglobin, which also bind with oxygen, but the hemoglobin really just acts as a source or a sink of oxygen. The equilibrium between the gas and the liquid portion of the blood is only dependent upon the PO2 and the dissolved oxygen concentration. So from thermodynamics, we know for gas-liquid equilibrium we can use what's called Henry's law, which I have written right here, which for the case of oxygen as our solute would say that the PO2, or the partial pressure of oxygen in the gas phase, given by the total pressure times the mole fraction of oxygen, would equal Henry's constant times the dissolved oxygen concentration. And one of the confusing things about oxygen transport in the medical literature and in biomedical engineering that you'll have to wrap your head around is a lot of times, rather than talking about the concentration of the actual oxygen in the dissolved liquid phase, you may see people just use the PO2. So the PO2 is actually the amount of oxygen in the gas phase, but from Henry's law you can see that we can interchange back and forth. If we know the Henry's constant, then when we say a situation has a PO2 of 120 millimeters of mercury, for example, if we divide that number by the appropriate Henry's constant, we would then have the dissolved oxygen concentration. So you'll have to be able to work with this equation in problems, and you'll see this happen as we go through the solutions to certain situations. Now the Henry's constant is shown in this table right here. Here's a table that presents the Henry's constant for oxygen in water at various temperatures. And in my book, the units I like to use for my Henry's constant is I like to use millimeters of mercury for the pressure and micromolar for the oxygen concentration. Different folks use different variables, and that's just another part of engineering analysis is that you might see other people using different concentrations, and you would just have to be able to convert back and forth. But one of the things this shows then is, since the concentration of oxygen, say in water, is what this says is that it's directly proportional to the PO2 from Henry's law and inversely proportional to the Henry's constant. So you can see at low temperatures the Henry's constant has a much smaller value than it does, say, at higher values, and this accounts for the higher solubility of oxygen in water at lower temperatures. Now the Henry's constant for oxygen in water is given in that table, and you're probably wondering, well, what is it for blood? And with the PO2 in millimeters of mercury and the Henry's constant in micromolar, for blood at 37 degrees C, a good number for the Henry's constant is 0.74 millimeters of mercury per micromolar. Now, we're pretty sophisticated organisms in terms of how we transport oxygen throughout our body, and if it was just by diffusion alone, we wouldn't be able to exist. Oxygen can only diffuse a couple hundred microns from its source before the cells would totally consume that oxygen. And this is shown in figure 7.1. This is the PO2 profiles of Brockman bodies. Brockman bodies are specialized clusters of cells found in fish that secrete insulin, and there was great interest at one time because of the fish farming industry to harvest the Brockman bodies from fish and use those as a means to provide insulin to people with diabetes. So these Brockman bodies would be encased in an immunoprotective barrier, and they would produce fish insulin in response to changes in the body's glucose values. So what these guys did is they did some really clever experiments. They basically isolated a Brockman body, which is about 800 microns in diameter. So that's what the BB stands for, Brockman body. And the dashed line would just be the boundary layer or the mass transfer film that surrounds the Brockman body. And they held that Brockman body in place in a nutrient media, as shown here. And sometimes they would turn on a little mixer to get some agitation, get some convection around the Brockman bodies, and in other cases the fluid surrounding the Brockman body was stagnant. And then they had a very fine micro PO2 probe that is connected to suitable electronics and a metering device, and they were able to move that probe not only through the boundary layer and measure the PO2 in the boundary layer surrounding the Brockman body, but they were also able to measure the PO2 values within the Brockman body. And I've taken their data and reproduced it on this graph. And this vertical dashed line right here, this would represent the cell surface of the Brockman body. So that's the interface between the Brockman body and the surrounding fluid. And then down here we have radial position. So this radial position is the distance from the center of the Brockman body. The abscissa doesn't go all the way to 0. You can see it stops at 100 microns here. But you can see the Brockman body has a radius of 400 microns. So in the case without any agitation for stagnant fluid surrounding the Brockman body, when they measured the PO2 within the Brockman body, they obtained the data shown by the open diamonds right here. And what's happening here is as the oxygen diffuses into the Brockman body, it's also being consumed by the Brockman body. And we can see that very clearly right here. If at steady state, if there were no reaction going on within the Brockman body, if there was no oxygen consumption, then this profile would just be flat. It would just be at equilibrium with the surrounding fluid. Also, they were able to measure out away from the surface of the Brockman body and measure the PO2 in the boundary layer. So you can clearly see the boundary layer change of the PO2 in that region defined by the dashed line, in that region between the dashed line and the surface of the Brockman body. When they added a little bit of agitation and got some convection around the Brockman body, you can see that the PO2 levels within that mass transfer film or boundary layer increase significantly. So you can see the enhanced mass transfer that happens in that particular case. And the higher values of oxygen in the surrounding boundary layer then leads to higher oxygenation levels within the cell body itself. So this is very interesting data, and actually we're going to use this data to develop our first mathematical model of oxygen diffusion within a spherical collection of cells. And a couple things that it shows number one, how we use the PO2 to represent really the concentration in the fluid phase and in the tissue space as well. And it also shows that, for the most part, you're out of oxygen not too far into the Brockman body. So what that means is that in order to have complex animals like us, we need a circulation system to deliver oxygen efficiently and quickly throughout the whole body. And that's the role that hemoglobin has. And after we get done discussing the diffusion and reaction model for the spherical Brockman body, we'll start talking about the role of hemoglobin. So what we want to do then is take this situation here and these data, and we'd like to find at what rate do these cells in here actually consume oxygen. In other words, from this data, can we make a prediction of what the oxygen consumption rate is within the cells? And that's what's talked about in this next section here, oxygen transport to a spherical volume of cells. We can develop a reaction diffusion model that can be used to describe the PO2 profiles that are shown in figure 7.1. So let's see how we would do that. So at the top of the next page, what we do is we perform a shell balance, take a spherical volume of cells, imagine a spherical volume, and then take a shell from R to R plus delta R, and at steady state, if you do a steady state oxygen balance across that shell, using Fick's first law is the only way that oxygen enters the shell and leaves the shell, we could write the following equation. So at R plus delta R, this term here would represent the rate at which oxygen is entering that shell of thickness delta R. Notice in spherical coordinates the surface area is 4 pi r squared. Also notice that the diffusivity, we have to use an effective diffusivity for oxygen because we're diffusing through tissue in the Brockman body, and that effective diffusivity for tissue, recall from chapter 6, that we call dT. And C, oxygen, would be the concentration of oxygen within the spherical volume that we're talking about. So this is the rate at which oxygen comes in by diffusion. This is the rate at which oxygen comes out of that shell volume by diffusion. And that difference in the oxygen, if there's a difference, then that means oxygen got consumed by those cells. And we write the oxygen consumption as shown here. So the volume of that shell would be 4 pi r squared times delta R. And then we introduce the cell volume fraction. So phi would be the volume of the cells per that total volume, 4 pi r squared delta R. And then gamma oxygen, the capital gamma oxygen, this is our oxygen consumption term, which would be the amount of oxygen that the cells consume per volume of cells. So this is all properly normalized then to the situation that describes the oxygen consumption. Let's see, going down into this next paragraph here, let's see, there's a couple other points we need to make. Now the product of, did all that. dT is the effective oxygen diffusivity, I mentioned that earlier. That's going to be given by equations like equation 643 or 645. And for oxygen at 37 degrees C, Bentley gives a number for, a typical number for oxygen diffusion in tissue of 2.41 times 10 to the minus 5th square centimeters per second. Recall that in chapter 5 there was an example where we showed these Japanese guys did some experiments for water and came up with a diffusivity of 2.76 times 10 to the minus 5th square centimeters per second in water, and you can see it's reduced a little bit in tissue. It's not a very significant reduction because you have to remember that oxygen itself is lipid soluble, so the oxygen is not only going into the cell and reacting, but it can also easily diffuse through the cell with a little bit loss of diffusivity just due to the more viscous style of cells are different than water, so there's more diffusion resistance in a cell than through water. Okay, so let's see, the units on gamma oxygen that we'll use that are compatible then with the concentration. I like to use my reaction rate units for gamma oxygen to be micromolar per second. Okay, so if we now take equation 7.2, divide by delta R, take the limit as delta R goes to 0, and also this is where we bring in Henry's law and we can replace the concentration, the dissolved oxygen concentration, with the PO2. Remember, the PO2 is equal to Henry's constant times that concentration. And when you do all of that, you end up with equation 7.3, which then describes the diffusion and reaction of oxygen through a spherical volume of cells. In order to solve this second order differential equation, we would need a couple of boundary conditions. We need two boundary conditions. So by symmetry at the center of the sphere, we would have that dPO2 dr is equal to 0. And then at the surface of the sphere, we just call that PO2 at r equal to the radius of the Brockman body. And you'll see in a little bit how we relate the surface concentration to the bulk concentration of oxygen in the surrounding fluid. Now the oxygen consumption rate for tissue can be described by Michaelis-Menten type kinetics. You've seen Michaelis-Menten type kinetics in the bioprocessing lab when you talked about enzymes. If you take the biochemical engineering class in the fall, we'll spend quite a bit of time on Michaelis-Menten type kinetics for enzyme reactions. But in any case, you can write the reaction rate of oxygen in the cells like this right here. Vmax would be the maximum oxygen consumption rate when the PO2 level is large in comparison to the Michaelis constant case of M. Now it turns out that in most cases for oxygen consumption by cells, the Km, the Km value is actually much smaller than the PO2. For example, for islets of Langerhans, which have the cells, the beta cells in your body that produce insulin, the value of Km has been measured to be 0.44 millimeters of mercury. And within your body, PO2 in tissue typically ranges from 10 to 100 millimeters of mercury. This is sort of the physiological range. So with that low value of Km and the larger values of the PO2, we can pretty much approximate the oxygen consumption rate of cells or tissue by the Vmax value. And what that means then is that the gamma oxygen is a constant, and that means then that the whole right hand side of this equation over here is also a constant, and this just becomes an easy double integration to find the PO2 profile within the spherical volume of cells. Now there's a couple things that you might find in the literature you just have to be aware of, is that Vmax is often expressed as the oxygen consumption rate on a per cell basis, and rho cell is the cell density, that is the number of cells per total volume. So if you think about it, then what that means is phi times what we call gamma oxygen is also equal to rho cell times Vmax, when Vmax is expressed as the oxygen consumption rate on a cell basis. And phi, recall, is the volume fraction of the cells within that total volume. So in terms of the volume of a single cell, that is V cell, if you know the radius of the cell and assume the cell is spherical, the volume of a cell would be 4/3 pi r cubed. Then we also have a relationship between what we call the cell volume fraction and the volume of a cell and that cell density. Okay, so with gamma oxygen a constant, we can then go ahead and integrate equations 7.3, apply the boundary conditions, and then we obtain equation 7.6, which tells us what the oxygen profile looks like within the spherical volume of cells. And everything in here you would know, as the engineer, you would know all these parameters over here if you knew the oxygen consumption rate, the cell volume fraction, the diffusivity or Henry's constant. You would know all of these guys, and if you knew what the concentration of oxygen happened to be at the cell surface, then this equation would predict what the oxygen level is within the spherical volume of cells. And of particular interest to you would be what's the value at the center of that volume of cells. You know, the question being, do you run out of oxygen before you reach the center of the cells? Now, if we have an external concentration boundary layer in the fluid phase surrounding the cells, as shown in the earlier figure 7.1, then we have to take into account the external mass transfer resistance by incorporating the mass transfer coefficient into equation 7.6. Now if you have really good mixing in the external fluid, your Km is going to be really large, and what that means is the PO2 at the surface is just going to become the PO2 in the bulk solution. But as shown in figure 7.1, even with the case of some convection around the Brockman bodies, there's still significant diffusion resistance in that fluid film that surrounds the Brockman body. So we need to account then, in order to analyze data like shown in figure 7.1, we need to account for the external mass transfer coefficient. And what this will allow us also to do then is to relate the PO2 at the surface of the Brockman body through the mass transfer coefficient to what the bulk concentration of the PO2 is in the surrounding solution. And at steady state, we can get to that relationship by recognizing that the rate of oxygen diffusion to the Brockman body has to equal the rate at which the Brockman body consumes oxygen. And with that word equation, we can then apply our math to that, and the oxygen diffusion rate to the surface, the mass transfer rate to the surface, basically your m dot A would be the surface area, which is 4 pi r squared, times the mass transfer coefficient, times the difference in the concentration of oxygen between the bulk solution and the oxygen concentration at the surface of the Brockman body. And this oxygen diffusion rate has to equal the oxygen consumption rate, and that's going to be the volume of your Brockman body, which is 4/3 pi r cubed. That's the total volume. Multiply that by phi, which is the volume fraction of the cells, and that would then tell you the actual volume of the cells, and then multiply that by gamma oxygen, because this is the oxygen consumption rate based on the volume of the cells. So one of the things we can get from equation 7.7 then is we can now solve for the oxygen concentration at the surface of the cells, and then we can put that into this equation up here, and then we'll have one big equation that describes oxygen transport in those in the Brockman body. So if we take this equation then and also use Henry's law to replace the oxygen concentration with the PO2, we then get equation 7.8, which is the PO2 at the surface of the Brockman body. And notice that that value depends on the bulk concentration, and that bulk concentration PO2 gets reduced because of the mass transfer and oxygen consumption effects. Notice that if the mass transfer coefficient is really large relative to the oxygen consumption within the Brockman body, this term here goes to 0, and the PO2 at the surface of the Brockman body becomes the bulk concentration, as I mentioned before. So when you substitute that back into equation 7.6, we get the final equation here, which describes the PO2 profile within the Brockman body, recognizing that this term right here is just the PO2 at the surface. Now in the next example, in example 7.1, what we're going to do is we're going to take equation 7.6, and we're going to use that to find from the given data for the internal PO2 profile that was measured for the Brockman body. We're going to do that and find out what the oxygen consumption rate of the Brockman body cells happens to be. So what we're going to do is we're going to use the diamond symbol data shown in figure 7.1 to estimate the oxygen consumption rate of the Brockman body. So this is the case without any convection. And we're going to find from that analysis the gamma oxygen. We're going to assume that the volume fraction of the cells in the Brockman body is about 0.85, which is a typical volume fraction in tissue, connective tissue. We'll also compare the predicted value of the PO2 at the surface of the Brockman body from equation 7.8 to the value given in figure 7.1 that you can read off from the graph. We'll assume the Brockman bodies have a diameter of 800 microns and that the Henry's constant for oxygen for the nutrient media that's used is 0.7 millimeters, 0.7 millimeters of mercury per micromolar. And our solution strategy, if we go back and we look at equation 7.6, you can see that if we plot the given PO2s that are given in figure 7.1 and we plot that versus the bracketed term, if you plot the PO2 not versus the radius but versus the radius normalized to the radius of the Brockman body and subtract that and square that and subtract that from 1. So basically if you plot the PO2s versus the bracketed values, you should get by this equation a straight line, and from the slope of that line you'll be able to extract the value of the gamma oxygen, and the intercept of that line would be your PO2 at the surface of the Brockman body. So what we do then is we go to the graph and we carefully read off radial positions within the Brockman body in microns, and then we read off the PO2 values as I've got written right here. And then we perform that linear regression of the data using equation 7.6 as I just talked about, and then we plot the PO2 versus this bracketed term here, and it should be linear with a slope m equal to this quantity right here and a y-intercept equal to the PO2 at the surface. Now figure 7.2 shows the results of the linear regression. So we go down here, we can see the results of the linear regression right here, and the data is remarkably linear, which is really exciting if you're in the transport phenomena to see that it's linear. And from the slope of that we can determine the value of the oxygen consumption rate of the Brockman bodies. And that's what's talked about next then right here. We see then that the slope is found to be equal to minus 47.6456 millimeters of mercury. Now in order to determine the value of gamma oxygen, we need to estimate the value of dT for oxygen, and here we'll use the value that Bentley gave of 2.41 times 10 to the minus 5th square centimeters per second. So from this equation we then solve for the gamma oxygen as shown right here, plug in all the numbers, all the units, and we end up with a gamma oxygen level of 7.24 micromolar per second. Now from figure 7.1, the PO2 at the surface of the Brockman bodies, based on their data, would be 57.6 millimeters of mercury. That's the actual experimental value. From the linear regression of the data in the table, the y-intercept is found to be 53.51 millimeters of mercury, which is the same as the surface value of the PO2, and this value does compare reasonably well with the measured value of 57.6. So it's off by maybe 4 millimeters of mercury, about a 7-8% error, which really isn't bad. We can also use equation 7.8 to find the value of the PO2 at x equal to 0. And we can do that if we go back to figure 7.1, we see that the PO2 in the bulk solution is 140 millimeters of mercury. Now it's important to note that if you have air at 1 atmosphere and air contains 21% oxygen, then the maximum PO2 you could ever get in a saturated solution of, say, water at 1 atmosphere would be about 160 millimeters of mercury. So you can see they're a little bit below that saturation value in terms of their PO2 in the bulk solution. Also, for a sphere of cells like the Brockman bodies in a stagnant fluid, which we're talking about in this case, the Sherwood number is going to be 2. So assuming the nutrient media is mostly water and we take that DAV then for oxygen to be 2.76 times 10 to the minus fifth square centimeters per second, a value that we talked about from chapter 5. Then from the Sherwood number for a sphere, we can calculate the value of Km, which I show right here, gives us about 6.9 times 10 to the minus fourth centimeters per second. And then from equation 7.8, now this here was the relationship we obtained by equating at steady state the external mass transfer rate to the oxygen consumption by the Brockman body cells. So when we do that calculation and we use equation 7.8, plug in all the numbers, here we predict a surface value of 56.76 millimeters of mercury, which is almost spot on to the actual experimental value. So this problem shows you how we can use a reaction and diffusion model in spherical coordinates, analyze data that's been found for a actual spherical volume of cells, and extract from that data of the PO2, we can find the oxygen consumption rate of those cells. Now, as I mentioned earlier, in more complex organisms like large vertebrate animals and so on, oxygen just cannot diffuse far enough on its own to sustain a body of cells the size of each of us. So what that means is that nature had to come up with a way to actually circulate and carry a lot of oxygen throughout the body. And if you look at the oxygen consumption rates that are required, and you look at the solubility of oxygen in water, water itself does not carry enough oxygen to sustain our lives. So that means we have to have a special source of oxygen, something that can carry a large amount of oxygen within the body. And that's taken up by the role of hemoglobin, which I show in this little cartoon down here. And the important thing about hemoglobin is called hemoglobin A. That's the adult form. And hemoglobin consists of 4 polypeptide chains. And a polypeptide chain would just be a polymer of amino acids. And 2 of one kind called the alpha chain. So there's 2 alpha chains, and then there's 2 what are called the beta chains. And these chains are connected together to form the hemoglobin molecule. And the hemoglobin molecule is nearly spherical in shape with a diameter of about 5.5 nanometers and a molecular weight of 68,000. Now, the oxygen binding capacity of hemoglobin depends on the presence of non-polypeptide units called the heme group. And I show a heme group on each one of these polypeptide chains. And the iron atom within the heme group gives blood its distinctive red color. And the heme group is also called a prosthetic group because it gives the hemoglobin protein its overall functional activity. Now each of the heme groups can carry 1 molecule of oxygen. That's going to be the important thing here. And that organic part of the heme is called the protoporphyrin. And what's important here then is that a heme group can bind 1 molecule of oxygen. Now over here on the side I got a little sidebar calculation I want to show you here, is that nominally in a healthy person the level of hemoglobin in the body is 150 grams per liter of blood, or 15 grams per deciliter of blood. If you divide the 150 grams per liter by 68,000, then we can say that the concentration of hemoglobin in molar units in blood would be 2200 micromolar. Now, since each molecule of hemoglobin can carry 4 molecules of oxygen, that would mean that when hemoglobin is saturated with oxygen, and we write that as HBO sat, that would mean then that the maximum amount of oxygen that can be carried by blood is 8,800 micromolar. So this is what we mean by the saturation value. And a particular value of hemoglobin in the blood at some PO2 we call HbO. Okay, so the HbO, which is going to depend on the local PO2 in the blood, is defined as Y, the saturation fraction, times the hemoglobin saturation. Or you could say that the amount of oxygen in the blood carried by hemoglobin is equal to the saturation fraction times the 8,800 micromolar, being the nominal healthy value of hemoglobin in a human being. Now, the way we describe oxygen binding with hemoglobin is through what's called the oxygen-hemoglobin dissociation curve. So the binding of oxygen with hemoglobin is described by a figure 7.4, which we'll get into in a moment. And it's important to realize that this is an equilibrium curve that expresses for a given oxygen partial pressure, or PO2, the fractional occupancy of the hemoglobin oxygen binding sites on a large number of hemoglobin molecules. That's the saturation fraction. The equilibrium partial pressure of oxygen above a solution of blood, recall, is related to the dissolved oxygen concentration by Henry's law, which we gave earlier by equation 7.1. So in equation 7.1, H oxygen is Henry's constant, and a good value for that at 37 degrees C, as I mentioned earlier, was 0.74 millimeters of mercury per micromolar. And C oxygen is the dissolved oxygen concentration. Here we'll use units of micromolar in the blood. And it's a very important, to keep this in your brain and never forget it. But it's very important to realize that the PO2 is exerted only by the dissolved oxygen. The equilibrium relationship is between the dissolved oxygen concentration and the PO2 in the gas space. Oxygen bound to hemoglobin does not directly affect the PO2, but only serves as a source or sink for oxygen. So folks have done these equilibrium experiments, taking volumes of blood, putting them at equilibrium with a known amount of oxygen in the gas phase, and then they measure the dissolved oxygen and they measure the PO2 in the gas space. So down here on this hemoglobin, or this oxygen hemoglobin dissociation curve, the abscissa, we have the PO2 in millimeters of mercury, running from 0 up to 120 millimeters of mercury. Remember, I told you earlier, at 1 atmosphere with 21% oxygen, the highest this value would be 160 millimeters of mercury. Physiologically, we can't really get that high because of dilution effects and so on in the lungs. So typically these curves end at 120. Over here on the ordinate we have the fractional hemoglobin saturation, which we call Y. So this fractional saturation, which depends on the PO2, if you take this over here and multiply that by the 8,800 micromolar right here, multiply that, that's how you get the amount of oxygen that's being carried by the hemoglobin. And the normal physiological range for the PO2 in your body ranges from about 95 millimeters of mercury. Okay, that would be about the maximum PO2 that you have in the air in your lungs that's interacting with the blood. And you can see at 95 millimeters of mercury, the saturation value is about 0.95. And then, so this would be like your arterial blood, 90 to 95 PO2, and venous blood's down here at around 40. So you'd be at around 75% saturation for venous blood. If you're exercising those muscles and so on, you might get down to about 20 millimeters of mercury. But generally, the operating range for the human body is 40 to 95 millimeters of mercury. In fact, it's interesting in some of these COVID patients that need to go on respirators. I heard the doctors talking about people having saturations down around 45%, which is really frightening, because that means they're like basically out of oxygen compared to what you would find in a normal patient, where their saturation values should be up around 90 to 95%. So that's the oxygen hemoglobin dissociation curve. And basically the way you use it is you say, okay, if my PO2 is, say, 60 millimeters of mercury, I would go up and read off my saturation, which in this case might be about 0.88, and then multiply that by the 8800, and that'll give you the amount of oxygen being carried by the hemoglobin itself. At that same PO2, the amount of oxygen that's actually dissolved in the solution would be the PO2 divided by the Henry's constant. So if you took 60 millimeters of mercury and say your Henry's constant is on the order of 1 millimeter of mercury per micromolar, we know it's 0.74, but just, for sake of argument, let it be 1. Then you can see that the amount of dissolved oxygen is only 60 micromolar. So you can see that the amount of oxygen that's carried in the body, dissolved in your plasma, is negligible compared to the amounts that can be carried by hemoglobin. And because of that, that's why we're all here today. If it wasn't for hemoglobin, we wouldn't be here. So we really should give the hemoglobin a round of applause. Okay, so that's all we have for this lecture. We'll come back and pick up where we left off on the oxygen hemoglobin dissociation curve. And what we'll try to do next time is I'll show you how we can transform that curve into an equation that we can use when we're trying to design oxygenators and things like that.